Alright, so we're going to start our unit on light and energy today. And we'll jump right in here. The classical description of light. Light is basically an electromagnetic wave that consists of some elementary particles that we call photons. And basically a photon is a little packet of energy that can carry electromagnetic radiation. And the way we measure these things is with what we call an electromagnetic spectrum, which we abbreviate EM. And the diagram of it is on page 120 in your textbook, and it'll list all the forms of the radiation. And in basic, when we've talked about some radiation in the past, back in nuclear chemistry, but radiation is basically a form of energy that exhibits wave-like behavior as it travels through space. So when you think of waves, most of us are thinking about waves at the beach, waves in the ocean. Yes, they're very, very similar, but not exactly. They have some same characteristics that we'll talk about. And here are some of those characteristics. We have first one, and we start talking about light as a wave. You've got wavelength, frequency, and amplitude. Wavelength, which is abbreviated by that weird symbol right there in the parentheses, is basically the distance between two crests, crest being the top of the wave, or two troughs, which would be the bottom of the wave. So we're measuring from one crest to the next, or we're measuring from one trough to the next to figure out how long that wave is. And you can see that here in the diagram right here. This is wavelength here, and this would be wavelength here. Obviously, we can measure it from the top of this wave to the top of this one, or the top of this one to the top of this one, and still get wavelength. Frequency, which is abbreviated with V, that's the number of waves that pass a given point in 1 second. So if I was using, this point right here, how many waves past that point in 1 second would be my frequency. Amplitude, okay, this is showing you amplitude. That would be how high the wave rises from the middle of the midline. Okay, so we're measuring from the midline to the top of the wave. We start talking about the speed of the wave. Speed of light, okay, is always c, and c is always 3.0 times 10 to the 8th meters per second. So anytime you see speed, you can always sub in that for the speed of light. Frequency and wavelength are inversely proportional, which means as one increases, the other will decrease. And from that, all that information, we can derive a formula of C equals the wavelength times the frequency. We start talking about visible light, light that we see, and it's a very small part of the electromagnetic spectrum, and it can be separated into a continuous spectrum of light, which we call the rainbow. Everybody's heard Roy G. Biv before, right? Red, orange, yellow, green, blue, indigo, and violet. And basically what you need to know about that color spectrum is that red light has the lowest frequency and the least amount of energy. And we go all the way to the other end with violet light, and it has the highest frequency and the most energy of all those. Now, as we're going from red to violet, we're obviously increasing in frequency and we're increasing in energy. And when we start talking about the colors of light that we see, we take spectral lines, and those spectral lines are produced by colored light passing through a prism. And basically that prism breaks down the colored light into certain colors that we can see, and we can then determine what colors of light that we see, and now measure the wavelength and the frequency. Okay, and here is the electromagnetic spectrum. Obviously you can see there's that visible light, the rainbow that we talk about. Then you have radio waves, microwaves, infrared waves, ultraviolet rays, X-rays, and gamma rays, and those are all the different kinds of radiation that we'll be discussing. And notice that as we start at red and move to violet, that we are increasing in frequency and energy. And here's our wavelength. So if we're talking about wavelengths here, this is what we're talking about. And there's those different kinds of radiation in a chart, okay, showing you the different kinds of wavelengths. And if you were to ever be asked what order they come in from least to greatest, this is what a great way to remember that is that rabbits meet in very unusual, expensive gardens. Okay, it's kind of cheesy and silly, but it works, right? Because we all know that radio waves are have the smallest wavelength and the least amount of energy compared to gamma, and we can put them in order by saying that little phrase, you know, put them in the correct order: radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. And so here we can do, knowing our equation back from a couple of slides ago, C equals wavelength times frequency, C being the speed of the wave, the speed of light. Then we can plug in some things when they give us a word problem, like find the wavelength of blue light, if we know the frequency to be 6.4 times 10 to the 14th per second. And we can simply plug those pieces of information into our equation, substitute it in, okay, and then take 6.4 times 10 to the 14th per second, divide that on both sides to solve it, just like we would an algebra problem, and come up with the wavelength being 4.7 times 10 to the negative 7 meters. Okay. Light is a particle. Okay, so now we've talked about light as waves. We can also talk about light as a particle, and the energy of a photon can be calculated. Okay, when we start talking about light as a particle, that would be a photon, and that energy can be calculated by E equals h times v, which says that the energy of a photon is related to its frequency. Now h is what we call Planck's constant, named for Max Planck, who discovered it. And h is 6.626 times 10 to the negative 23rd joules per second. Okay? And so by knowing our two equations, we can then combine them. If we know that the speed of light is the wavelength times the frequency, we know that the energy of light as a particle is Planck's constant times the frequency, then we can then decide that combining those two equations and find the energy, if we only know the wavelength, okay? Because we know Planck's constant, we know the speed of light, we know h and c, and if we know the wavelength, we can then determine the energy, and I'll show you here, okay, in our calculation. So it says, what is the energy of X radiation with a wavelength of 1 times 10 to the negative 6 meters? So there's our equations, and there's our equations combined, and we plug them all in, and ta-da, 1.99 times 10 to the negative 19 joules. Remember, energy is always measured in joules. That's what capital J is. Okay? So all we did was plug in Planck's constant here for H, the speed of light here for C, divide by our wavelength that they gave us, and came up with an answer, and that's the energy of X radiation. Okay, now we're going to start talking about electrons in their excited state and their ground state. Okay, and when an atom absorbs heat or electricity, its electrons move to these higher levels of energy, and that's what we call our excited state. So, and then the original level where that electron starts is called the ground state. So, you've got this atom who has these electrons circling, and it absorbs some heat or some electricity, and as it absorbs that, these electrons get super excited, and they get a lot of energy, and they go up to higher energy levels. They go to that excited state, and from their ground state. And then what happens is, when they get to that excited state, they become unstable. And as they become unstable, they start to quickly fall back to where they came from, back to their ground state. And when they do that, this causes a release of energy, and when we see that energy, we see it in the form of light. And whatever color of light that is emitted depends upon how far the falling distance of that electron. So obviously, if it falls a greater distance, we see a different kind of light than if it falls a small distance. And we can determine, when we calculate the energy, how far that electron fell. Okay, again, like I said, falling distance is small, then little energy is released, which is obviously a different kind of light than if it's falling a large distance. Okay, we're not really talking about the questions here, I'll skip those, but that's basically your introduction to light and energy.